get incredibly accurate graphs, but bullet sketches that will help us to graph the function. So let's look at this first example. One thing that we like to know about the polynomial is its degree, and you find the degree by looking at the largest exponent in the polynomial. So here we have an exponent of 2 and of 1, and this one, 5, does not have an exponent at all, and an exponent of 3. So which is largest out of those? Well, the exponent of 3. So this is a degree 3 polynomial. Another thing we're concerned with is the leading coefficient. The leading coefficient is the number in front of that largest variable you just found. So here our largest variable is the x to the third. Negative 7 is the number in front of that. That is the leading coefficient. And it's called leading because typically we would write the function in order, largest degree to smallest, and the negative 7 would be in the front. But you do have to look for that largest exponent because sometimes they'll be a little tricky. The constant term is the term that doesn't have a variable with it. So that would be our 5 here. And the super cool thing about the constant term is that that's your y-intercept. Okay, now notice this is a polynomial written out. Nothing is factored. It's just completely written out. All right? Some of the questions are going to ask you about maximum and minimum or turning points. So if they say maxima or minima, okay, that's what they mean, are turning points on the graph. It may go up and down and up and down. Okay, a lot of important things come from knowing the degree, and one of those things is the number of turning points. Okay, the number of turning points that are possible, the maximum number, is your degree of your polynomial minus 1. Okay, so in this case, that would be 3 minus 1 or 2. The graph of this polynomial can have at most 2 turning points or 2 ups and downs, maximum, minimum. Okay, the minimum number of turning points depends on your degree also. So if the degree of your polynomial is even, or the degree of your polynomial is odd. Okay. If the degree of your polynomial is even, you have to have at least 1. If it's odd, there could be none. Now, they're saying there will be none, but there could be none at all. It doesn't have to have turning points if the degree is odd. So this function here might not have a maximum or a minimum at all. Okay, another thing we're concerned about when we're graphing is the number of zeros or the number of x-intercepts, because that gives us kind of a way to situate our graph. The maximum number of x-intercepts for a function, okay, is its degree. So in this case, this would have 3 at most. Not that it has 3, but it could have 3. The minimum number, again, depends on your degree. If the degree is even, it could have none at all. It doesn't have to have any if it's got an even degree. If the degree is odd, it has to have at least 1. And we'll talk in later sections about why that is. Okay? And when we say zeros, we mean real zeros, real numbers, okay, not imaginary ones. One more super important thing is the end behavior, okay? And the end behavior depends on both the degree and the leading coefficient, okay? So we have 4 cases that could happen. For D, I'm going to put degree just to save room, and for leading coefficient, I'll put LC. Okay, if your degree is odd and your leading coefficient is positive, you'll have 1 case. If your degree is odd, let me resituate, sorry about the delay there. Okay, if the degree is odd, you could also have a negative leading coefficient, so we'll have to talk about that case. And then we have our evens. Okay, so we could have an even degree with a positive leading coefficient, and we could have an even degree with a negative leading coefficient. Okay, this is our end behavior. This tells us what happens at the ends of the graph as it goes off into infinity. What is happening? Okay, where is it going as it goes off into infinity? Okay, so those are our 4 cases. Here's the first one. If it's odd and positive, every single time, if it's odd degree and has a positive leading coefficient, this is the end behavior. It will go up to the right and down to the left off into its infinity. Okay? If it's odd and has a negative leading coefficient, like our example here, the end behavior will go up to the left, it switches, and down to the right. And this is something I just want to take notes on, okay? Until you get it memorized. The even degree, remember parabolas? They're even degree. What do they do when they have positive in front? They go up and up. Okay, evens go the same direction. And what happens to a parabola when it's negative in front? Hopefully remember, it goes down and down because that's even. Okay, so this is what the end behavior looks like. Okay, we're going to talk about how to describe that because they describe it in kind of a technical way. So let me clear the slide and we'll talk about how you describe each of these. So here was our first case, and the way we describe them is we say what happens as x going positive infinity and what's happening as x is going to negative infinity. Okay, that's how we describe them. For this graph, as x goes to positive infinity, in the right quadrant here, what's happening to f of x? Is it going up or down? It's going up, which is positive infinity. And then we would say what happens when x is negative infinity? It's going to the left. Well, f of x is going down, so that's negative infinity. Okay, and this was for odd degree, right? And a positive leading coefficient. Let's look at our next case. I know this is kind of a confusing way to describe things, but that's just the way it's described. Okay, let's go with our next case where we have odd degree and a negative leading coefficient. Okay, we talked about that goes up to the left, down to the right. And again, we describe it in terms of as x goes to infinity, what happens to f of x? Okay, as x goes to positive infinity, which is on the right side. Okay, so here, what's happening to f of x is going down or to negative infinity. Okay, and as x goes to negative infinity, or over on the left side of the graph is where our negative x's are, what's happening to y? It's going upward or to positive infinity. Okay, let's talk about when we have even. And a positive leading coefficient, we talked about that's like a parabola. It goes up and up on each side. Let's talk about that in our technical mathematical terms. Okay, as x goes to positive infinity, or the right side of the graph, what's happening? F of x is going upward or to positive infinity. What happens as x goes to negative infinity, or the left side of the graph? F of x, or our y value, is pointing upward to positive infinity also. Okay, and again, you just want to take notes on these because I know at first it's like a foreign language to you. All right, what about when we have our last case, which is when we have an even degree and a negative leading coefficient? That's like a parabola with a negative in front, made it go upside down. That's what we have going on here. Let's explain it or describe it with our x's. Okay, as x goes to infinity, positive, or the right side of the graph, f of x is going down to negative infinity. And what happens on the left side of the graph? The same thing. Okay, so when it says describe the end behavior, that's what you're going to do. You're going to look at what the degree of the polynomial is, whether it's even or odd, and you're going to look at whether the leading coefficient is positive or negative, and then you'll write down the end behavior depending on that. So if you need to pause right here, you can pause to write this down. All right, so let's talk about this. What's the degree of this polynomial? So for review, degree is the largest exponent. So we look to find the largest exponent here, and it has an exponent of 6 is the largest, so it's degree 6. The leading coefficient is the number in front of that, so that would be 4. Now notice again, no parentheses here, because we're going to have some later with parentheses. The constant term is the number that doesn't have a variable, doesn't have an x. There isn't one, so the constant term is 0. Don't say none. It's not none. It's 0. We'll practice this one more time. What would the maximum number of turning points be? Okay, the maximum number of turning points is the degree minus 1, so 5. The minimum number of turning points, our degree was even. Okay, and we talked about what happens when it's an even degree and the number of turning points. What happens? It has to have at least 1. The maximum number of zeros is the degree, so there could be 6 zeros. There might not be 6 real zeros, but there could be. The minimum number of zeros, this could have none because it's an odd degree, or excuse me, an even degree. And the last thing we want to do is describe the end behavior of our graph. So again, let's look at we have even degree and a positive leading coefficient. So that was like our parabola that opens up because even degree, okay, so up and up. But we have to put it in the right terms of what happens as x goes to infinity and what happens as x goes to negative infinity. Okay, so the right-hand side of the graph, where x going to positive infinity, it's going up, so that's positive infinity also. As x goes to negative infinity, f of x goes to up again, positive infinity on that left side of the graph. So there is our end behavior. Remember, you can pause at any time or skip to another slide at any time. All right, you know how I've been warning you about factoring? This is factored. And the reason I warned you is because you do the degree and the leading coefficient a little differently. If we wanted to know what it was, we would have to FOIL, multiply all of this out, and that would take a while. There is a shortcut, however, that I'm going to show you. It's also shown in your book. To find the degree, what you do is you take the largest degree in each factor and multiply it together. You also want to watch for something. See that exponent there? That means there's 2 of those 3 t's. So we need to multiply that one twice. And this will help us get our degree and our leading coefficient easier than multiplying all those polynomials out. So I had a 2t and 2 3t's. 2 times 3 is 6. 6 times 3 is 18. And t times t times t is t to the 3rd. So our degree is 3 because of our exponent of 3. Our leading coefficient is positive 18. The constant term, again, to get that for sure, we'd have to multiply those polynomials out. There is a shortcut, however. You just multiply the constant from each factor. And again, notice there were 2 of those, so we're going to multiply 2 4s. So we have negative 1 from that first factor times 4 times 4. Gives us a negative 16 is our constant term. This will be the y-intercept of our graph. Okay, we're not going to worry about turning points this time just to save us some time, but we do absolutely want to know our end behavior. So we had odd degree and a positive leading coefficient of positive 18. So what is our end behavior going to look like? Well, if we look back at our notes, it looks like this and this. Up to the right, down to the left. We want to describe that as x goes to infinity, f of x goes to positive infinity on the right, and negative infinity on the left. Okay, so we had degree 3, leading coefficient 18, constant negative 16, and there's our end behavior. All right, we're going to take a